Hi, I'm Zhitong, and I'll present our work, Superpixel-guided iterative learning from noisy labels for medical image segmentation. This is a joint work with Shuailin and Xuming. Segmentation annotations often include a varying amount of noise in the medical domain. As shown in the following figures, the blue curves indicate human annotations and the red curves show potential annotation errors. Due to the memorization effect, learning from those noisy annotations has been particularly challenging for deep segmentation networks. Previous work can be largely grouped into two categories. The first type of methods that view the annotation of each image as either clean or corrupted are unable to fully utilize the pixels with clean annotations in each image. The second group considers the segmentation as a pixel-wise classification task and ignores the pixel correlation and spatial prior in image segmentation. In this work, we aim to exploit the structural constraints in the label masks and to fully utilize reliable labels for effective learning. To achieve this, we adopt a superpixel representation and develop an iterative learning method that jointly optimizes the network parameters and refines noisy labels. As an overview, we use superpixels as our guidance in an iterative learning procedure, alternates between a network updating stage and a label refinement stage. Specifically, given noisy training data, we first compute the superpixel of the input images. We assume the pixels share similar ground truth labels in each superpixel, which enables us to enforce the structural constraints on the label masks. More importantly, we treat each superpixel as a data sample in the subsequent iterative learning. This allows us to estimate noise level more reliably by pulling the pixel information from each superpixel. We now present our iterative learning strategy based on the superpixel representation. For the network training stage, we follow the multi-well learning framework and jointly train two instances of the target segmentation network using partial data with small losses. To better select data samples with clean labels, we design a superpixel-wise loss that combines the loss values of two networks with an agreement-based regularization on superpixels. To avoid overfitting to label noise, we design an automatic stopping criterion for the joint learning based on the loss statistics of superpixels. After the network training, we then use the network predictions to estimate the reliability of superpixel labels and relabel a subset of most unreliable ones. After that, we replace noisy labels by refined labels and start the next iteration. We validate our method on two public datasets with simulated noise patterns and compare our method with several state-of-the-art approaches, including quotation tree network and GL3R. We use average dice over the last 10 epochs as the evaluation metrics. Here is the quantitative results on SSC dataset. At the mild noise setting, we perform the best and it's also close to the performance in the original data setting. As the noise increases, the performance of other methods decreases sharply, indicating the significant impact of label noise. By contrast, our method consistently outperforms them and maintains high performance, validating its robustness to different noise settings. Remarkably, in the extreme noise setting, our method still achieves above 81% and outperforms others more than 7%. In this figure, we show curves of test dice versus epoch. As can be seen, most methods first reach a high performance, then gradually decrease, indicating that the training is affected by noisy labels. In contrast, our methods demonstrate a consistent high performance, which verifies the robustness of our training method. Ablation study on our model components shows that changing superpixel to pixel representation brings a performance drop near 2%. This demonstrates the advantage of superpixel representation in learning with noisy labels. Besides, ablating selection module or label refinement module both lead performance drop, which validate both are essential for our robust iterative learning strategy. Welcome to our poster. Thank you.